Okay, let's unpack this. Imagine you're soaring through the skies, maybe 35,000 feet. The hum of the engine's just a comforting sound, and then bang, an alert flashes, fire warning. In that split second, hundreds of passengers are relying on you, on the systems. So how do aircraft actually prevent, detect, and, fight fires? And what exactly does a pilot need to know to handle something that critical? Today, we're taking a really deep dive into the fascinating world of aircraft fire safety systems and protocols. And this isn't just like general knowledge for aviation buffs. No, this is about understanding crucial, layered systems designed to keep everyone safe. And for many of you listening, this stuff is absolutely essential for your ATPL theory exams. We know you need this. We've got a detailed guide here, basically a master class in fire detection and protection. It covers, well, everything from the science behind spotting a flame to the very specific drills pilots have to execute, like a blueprint for the worst-case scenario.
It really is. And what's truly fascinating here, often maybe overlooked, is just how deeply safety is woven into the aircraft's design right from the start. It's not some add-on, it's absolutely foundational. So we're going to explore these layers of defense systematically. From the physical bits, like containing a fire in a specific zone, to the really complex electronic systems, the aircraft's sort of nervous system for heat and smoke. And understanding each part isn't just, academic. It's vital for real-world operational safety and, yes, absolutely vital for nailing those critical theory questions you face in your exams.
Right, so our mission today is to distill all this detailed information into clear, actionable knowledge. We want to pull out the absolute must-knows and make sure you walk away not just, informed, but genuinely feeling prepared. Let's start at the very beginning. Our source material kicks off by saying aircraft are designed to be intrinsically safe, which sounds great, but it quickly adds they must always cater for the worst-case scenario. And that right there is where these fire detection and protection systems jump in.
Exactly. That concept of a designated fire zone is fundamental. To grasp this, think of these as specific areas within the aircraft where there's just an inherent risk of fire. We're talking engines, obviously, APUs, auxiliary power units, and even the main wheel wells, places with hot components, flammable fluids, potential leaks.
Okay.
So to prevent fire spreading out of these zones, they're isolated by what are called fireproof bulkheads. It's a core design philosophy, really critical, contain the risk.
That makes sense. And sticking with definitions, the source brings up the triangle of fire. Now, some of you might know this, but for those who don't, what is it and why does it matter here?
The triangle of fire, yes.
Yeah.
It's sometimes called the tetrahedron if you add the chemical reaction, but basically it's the three things you absolutely need for a fire: fuel, oxygen, and heat. Take away any one of those and you can't start a fire, or you can't sustain one that's already burning. Simple as that. And aircraft fire safety systems, they're all designed around breaking that triangle, removing the fuel source, cutting off the oxygen, or cooling things down below the ignition point. Understanding that helps you understand why different extinguishers work the way they do. It's the foundation.
Got it. Now, here's a key operational rule the source points out right away, and it seems a bit counterintuitive. A fire detection system needs to be fast, but it must not automatically operate the fire extinguishers.
Yeah.
Why separate detection and action like that?
That's a really important point, and it comes down to, well, false alarms and the need for human verification. Imagine a sensor glitch, maybe a temporary overheat that isn't a real fire.
Okay.
If the system just automatically blasted the extinguisher, you'd waste a very limited resource. You typically only get 1 or 2 shots per engine with those fire bombs.
Okay, only 1 or 2.
Exactly. Plus, discharging often triggers an automatic engine shutdown. You don't want that happening unnecessarily. So manual activation ensures the pilots confirm the warning, maybe check engine instruments, then take action. It's about balancing speed with certainty. Human in the loop.
That makes perfect sense. So how do aircraft actually see or sense that fire or overheat then? The source outlines 4 main ways. Let's start with the older tech, melting link detectors.
Right, melting link detectors. These are pretty basic. Think of a small plug made of a...
All right. Many thanks for listening to this free part of the ATPL Theory podcast. If you want to continue learning and access the full comprehensive guide, go to my Patreon at patreon.com/ATPLtheory or my Hero at herohero.co/ATPL. That is patreon.com/ATPLtheory or herohero.co/ATPL. Wishing you all the best.